Okay, sorry, excuse me. So I want to look at finding arc length and surface area if you are giving if you are given like a parametric set of equations, and it's actually a pretty it's a pretty easy proof to show, especially since we have already found how to find arc length just in general, right? So our arc length formula that we just looked at, I'll write it over here for the side. There we go. So our arc length would be, the integral from a to b of the square root of 1 plus f prime of x as a quantity squared dx, right? So we've already done that. If we have something that's represented by a parametric set of equations, and they're just calling it a smooth curve, right? So it's smooth. It's not discontinuous. There's no gaps or anything like that. And it can't intersect on itself except for maybe at the endpoint. So if it's a closed, like if you have a circle that's been defined parametrically, that's still going to be okay because it's really just the endpoint would have been an overlap. What you don't want is something like this where it comes in on itself. Then we can't use this. And you take a look at the formula, it's the derivative of x with respect to t squared plus the derivative of y with respect to t squared square root. It's very, very straightforward. And like I said, we can prove it very quickly. And then if you have surface area, if you're revolving it around either the x-axis or the y-axis, or we can extend that to any vertical line or any horizontal line. What I want you to take a look at is, again, it's sort of like that radius times that arc length. So we still have the arc length here, right? There's still your arc length. That doesn't change, just like normal finding surface area. But notice what does change or what is different. Or I guess in a way, the difference between the two formulas. This one has g of t. This one has f of t. And if you're wondering, well, what is g of t? What is f of t? If you read carefully at the beginning, g of t was the parametric in term like with y, where f of t was the terms of x. And notice their placement. G of t, which we remember said was y, when you're going around the x-axis. And that should make sense because if you revolve something about the x-axis, like, oh, here's your arc, whatever that looks like, right? If you revolve it around the x-axis to get its image over here, right? Remember, we're looking at the surface area of this, right? So there's that, right? The radius of the revolution, if you think about, bad color, there you go. The radius of the revolution here, like that radius there, right? That distance, top to bottom, that distance is a length on the y-axis, right? This distance right here. So when you're going about the x-axis, your radius should be in terms of y, because that's measuring that height. And then similarly, if you're going around the y-axis, right? So now if I have some kind of curve, then I'm going over the y-axis, same idea, that your radius is going to be measured, from that rotation out, and that's an x distance, right? So that radius should be in terms of x. So real quick, the proof then, how do we show that that's actually the, we'll do the arc length, and then the same principle would have applied to to the surface area, but you just start with your formula, right? So if we start with what we talked about arc length, we know that our arc length, I guess call it S, is equal to the integral from a to b of the square root of 1 plus the derivative, f prime of x as a quantity squared. Okay, so now write the derivative in terms of dy dx. So a to b square root 1 plus dy dx as a quantity squared. So again, we're just representing the derivative just a little bit differently. Now, certainly dy dx could be represented. So I'm going to need a really big integral symbol here. So from a to b of the square root, right, of 1 plus. Now let's write that just kind of with respect to t as well. So remember, like, you can find dy dx parametrically by doing dy dt over dx dt, and as a quantity squared dx. And then so if we think about this, like if I had like a this complex fraction here, I can really think about this 1 as like dx dt over dx dt, right? Or dx dt squared over dx dt squared. So we'll do that next. They get that really long integral a to b. So what I'm going to do is think about, well, I'm going to think about that one first, as a dx dt over dx dt, and then find that common denominator. So dx dt, actually dx dt squared, I think I said that the first time, plus dy dt squared. And remember, like originally, this already would have had that denominator, right? dx dt squared, and I'm just making that fancy one. So that was dx dt squared. I'm just taking that one and making it like this, and like, oh look, they have the same denominator, right? So that's what I'm just going to put them together. So all over this denominator dx dt is a quantity squared. Well, you can already see what's happening in terms of dx dt squared, dy dt squared in the square root, right? I'm looking for my highlighter. There it is. So right. So here and here, we're already picking up our, what we need, the derivative of x and derivative of y. Now think about this. The square root of that will cancel the square, and if we think about, it's in the denominator, so when we take it out, we can multiply by the reciprocal of it. So then a to b, so we get like dt over like dx, and then it's the square root of dx dt squared plus dy dt squared dx. I'm realizing that this dx I forgot to put there. Okay, and then this dx and this dx, it's like that pseudo algebra. They cancel, so we get from a to b of the square root of dx dt squared plus dy dt squared, and then we can put our dt right there. Okay, which is exactly what we had. That's the surface area, but it's right there. There it is, right? And that component, like I said, just gets put here and gets put here when we start doing surface area. Now, don't ever have to replicate or reproduce that proof, but I just think it's good to know. So on this video, I'll do maybe an example or two just to demonstrate that. And really, I'm focusing on that setup. So you have to be given it parametrically. So we're looking for the arc length, and it gives you the interval, from 0 to 2. And the thing I should remind you, because I guess it's not very clear in this, but those should be the time values, right? Because everything's in terms of t. So when I say this interval from 0 to 2. I'm assuming that's a t interval. If it doesn't tell you that, then you have to kind of manipulate either the x or the y depending on what it was they gave you. Like if they told you these were x's from 0 to 2, then you'd have to say, oh, when x is 0, what is your t value? And then, when x is 2, what is your t value? So, but you'll be given the interval in terms of time, almost all the time. No pun intended. Okay, so enough talking. Let's do some calculus. So the integral from 0 to 2, the square root of, and remember it's dx dt squared. So maybe over here you want to say, hey, what is dx dt? Dx dt is 2t. And what is dy dt? Dy dt is 2. So it's dx dt as a quantity squared. So that's 2t squared plus 2 squared dt. Right? Or the integral from 0 to 2 of the square root of 4 t squared plus 4 dt. Now, there's a lot of integrals that we're going to come across right now that we might not be able to solve by hand. And this is one of those examples. We don't know how to do this one just yet. But we could put it into our calculator and find that arc length to be approximately 5.916. So some of the homework, you're going to definitely need that calculator to get that answer. And you're just putting it into your FNINT editor and just finding that particular arc length or the area. Or sorry, the antiderivative. Okay, let's do one more example. I think I've got example 2 on this. Yep, same thing. Okay, so find the arc length of the curve given by these two functions on the interval 0 to pi. And again, assuming that's a time, right? Like unless they tell us otherwise, that will be our time value. So I think it's helpful in the margin maybe to say what is dx dt. The derivative of 4 cosine would be negative 4, but there's a chain rule of 2, so negative 8 sine of 2t. And then 2 sine of 2t. So dy dt then is equal to the derivative. So it's 2 cosine with a chain rule, so 4 cosine of 2t. So then we go ahead and say our arc length. I don't know why I'm using S. In honors pre-calc, we've been using S. So that's just kind of where my mind is right now. I realize it's sort of confusing because an SA could be surface area. So sorry about that. So 0 to pi square root of dx dt is a quantity squared. So negative 8 sine of 2t is a quantity squared plus 4 cosine of 2t is a quantity squared dt. So that would represent the arc length. There's the integral, and then we would just type into our calculator. And then nice thing too, I should have mentioned last one. Just because I'm given it in parametrics, as soon as I know what the integral is, like it doesn't matter if it's represented in x, t, y, theta. You just like the context of that variable is in the problem itself. But in terms of actually evaluation, the calculator doesn't know that. So you could just type this in as if they were x's or t's or y, whatever. As long as this variable that you have in your function matches the variable that's with respect to. And so then I typed that in, and I got 19.377. Okay. So, like I said, oftentimes the integrals you won't be able to necessarily do by hand, at least not yet. We still have a few more techniques to learn. So, if you're getting the setup, sometimes that's all the questions are going to ask, and then you can just go to your calculator. And one thing I was thinking of too, parametrically, we actually study this in honors pre-calc. When you have something that's parametrically defined by cosine and sine, it's a circle unless the coefficients are different. Then it becomes an ellipse. So this is an ellipse that's stretched, 4 in the x direction and 2 in the y direction. So if you went, if you go 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 1, 2, and eliminated a parameter, what you have graphed would be an ellipse. So you would be able to find from 0 to pi, so halfway. Well, actually, it depends because our period is actually pi, so the whole way around the ellipse, like that entire circumference of that ellipse would be about 19.377. So, okay, so hopefully, going through those two examples, of applying that, made sense. And then the next video, we'll just look at just applying, the surface area and go from there.